Okay, so we're going to do part 2 now of these cardiovascular adjustments. Now, if you recall from the previous video, there are 3 things that we have to do or that our cardiovascular system has to do during exercise. We have to increase our sympathetic output to increase cardiac output. Okay, we have to make sure that we get cardiac output back to the heart. So as much as it increases, venous return also needs to increase by that much. And we also need to do a good job of redistributing blood flow so that this blood, this increased cardiac output, is going to the places where it needs to go. Okay, so with this, we're going to talk about VO2 max, and then we're going to talk about how we can determine that. Okay, so just to make sure that we're all on the same page, VO2 means oxygen uptake, or how much oxygen are we actually using at any one point. VO2 max would be the maximum amount of oxygen that we can use, that our body's able to use. Now I want you to look here. So we've got rest and we've got exercise. Okay, at rest, we might be delivering based on blood flow. Look at this one over here on blood flow, or this square here that I'm circling. That's kind of representing blood flow. So when we're resting, we need to deliver enough blood so that we get 4 of those circles to our tissues, okay, or whatever. Okay. But what's interesting is that we're only using 1/4 of the available oxygen at rest. However, when we exercise, we're increasing blood flow or cardiac output by up to 4 times. Okay. And now instead of only using 25% of the oxygen, we're actually extracting 75%. In other words, we're using 75% of the available oxygen. Okay, so we're increasing blood flow by 4 times. We're extracting 3 times as much oxygen. Okay, and so as a result, we have a 12-fold increase, or in this example, we'd have a 12-fold increase. Okay, so we can increase blood flow, we can increase extraction. Now, exercise, like we talked about, will increase heart rate. So resting heart rate might be as low as 28, might be as high as 100. That's pretty high. But for most of us, it's between 60 and 80. Heart rate max is something that you really can't affect that much. It just slowly decreases over time, right? And so we talked about that in the last video, is that 220 minus your age gives you a good estimate of what your maximum heart rate is going to be. And it's also important to remember that as we increase exercise intensity, our sympathetic nervous system activity will increase as well. And this is good because sympathetic nervous system increases heart rate, increases stroke volume, increases pressure. But there's a cost that comes to this, okay? Or at least there's a challenge. It has to do with filling time. So what happens to filling time during exercise? Okay, and the answer is, I don't have this on the slide, I didn't notice that before, but it goes down. Right? As heart rate goes up, filling time goes down. So if we keep everything else equal, and the only thing that changes is filling time, what's going to happen to stroke volume and cardiac output? Well, unless I make adjustments, that reduced filling time is going to cause a lower stroke volume, and then as a result, I'm going to decrease cardiac output. So how can we compensate for this? Well, I can increase heart rate. The problem is that decreases filling time even more. Okay, so I want you to kind of put that to the side for just a minute, but just remember, filling time, increased filling time that occurs, so increased heart rate leads to a decreased filling time, that will decrease stroke volume. That's not great for exercise. Okay, so now we've got end diastolic volume. Okay, remember, end diastolic volume is the amount of blood that's in the ventricle prior to contraction. Okay, and the relationship between end diastolic volume and stroke volume is, as end diastolic volume increases, so does stroke volume. Our cardiac muscle cells are designed in a way that the more they're stretched out, the stronger their contraction. Okay, now this can be altered if we have a sympathetic response. Okay, as you can see here, for a given end diastolic volume, if we have no epinephrine compared to epinephrine, stroke volume is going to be increased because the ventricle is going to contract harder. This will lead to an this won't change end diastolic volume, but it will allow us to get more blood out of the ventricle. And so we'll have a lower and systolic volume. Okay? And so you could make the argument that, yeah, we have the sympathetic response and more blood is getting out, but that also presents a challenge because now we're ejecting more blood than normal. We have to make sure that we get that blood back to the heart. So there are a couple ways we can affect cardiac output during exercise, right? So normally our ejection fraction, that's the percentage of blood that leaves the heart during a contraction, is about 50%. Okay, if we don't change how much we fill the heart up with or the ventricle up with, but we have a sympathetic response, so we give some norepinephrine, our ejection fraction is 74%. Okay, so we're getting even more blood out than normal. That's great, especially during exercise. Okay, but we can even make that greater if we fill up the heart more and we have a sympathetic response. And so we might do something like this 52% ejection fraction becomes 80% by filling the blood up more or filling the heart up with more blood and having a sympathetic response. So we've got this figure here, okay? And I'm sorry that on the left side we only have the trained one, whereas on the right one we have trained versus untrained. Now notice we'll start on the right side here. So we've got heart rate on the x-axis, we've got stroke volume on the y-axis. Notice the relationship between heart rate and stroke volume. Okay, when it comes to the untrained, there's really not a big increase in stroke volume, so their cardiac output's going to be severely limited, right? They go from 120 maybe up to 130, okay? Whereas in the trained individual, notice that the stroke volume is a little bit greater at a lower heart rate, but not only that, it increases linearly, okay, up until we get to, in this case, about 190. And so we have a 50% increase going from 130 up to about 190, 195. That would be close to 50%. Okay, so here we've got not even 10% or maybe 10% increase with the untrained, but in the trained, it's about 50% based on this figure. Not numbers I'm going to ask you to remember. And then also notice that with the trained individual, their heart rate max increases for a while, and then it starts to plateau, and then it starts to decrease. So I want you to think about, well, what's causing that decrease in stroke volume max? Okay, this is something we're going to talk about in class. Much easier to do, I think, than just me trying to lecture you through it. All right, so just to kind of summarize what that last slide was about. So stroke volume increases. This is stroke volume. So just to be clear, stroke volume increases with work intensity up to about 40 or 60% of max, and then it kind of plateaus. In highly trained elites, athletes, kind of people at the Olympics, maybe not quite that good, or they don't have to be, stroke volume might continue to increase all the way up to max, okay? And so this is good because this means we're taking advantage of that Frank-Starling mechanism. So what I want you to do before you come to class is think about, how can we get this stroke volume, how can we have high stroke volume despite the fact that our filling time is greatly reduced when we're at intense, near max, or max exercise?